It's kind of funny to me that we started out trying to develop a molybdenum alloy, and we ended up adding so much chromium, it's actually a chromium alloy. But having the molybdenum in there does still confer benefits because it boosts the melting point.
To the best of our knowledge, there's nothing that exists like it. So it's going to open up a whole new market of material for people who wants to look at 1600 degrees C operation of metallic-based systems.
Hi, I'm Brian Freshour, Intellectual Property Manager at WARF. I had the pleasure of working with these inventors to patent this Innovation Award nominated invention. If you have an invention you'd like to disclose to WARF, feel free to reach out to me directly or use the links below. Now stay tuned for more details on the nominee.
My name is Dan Thoma. I'm a faculty member within Material Science and Engineering at the University of Wisconsin-Madison.
My name is Michael Niezgoda. I am a research assistant in the Alloy Design and Development Lab here at UW-Madison.
We're looking at ways to make new alloys that are going to give us a boost in the energy economy. One way to do that is to go to higher operating temperatures. The jet engine will operate around 1100 degrees C. We're looking at going to 1300 degrees C, or for hypersonics, or for fusion energy, for first wall diverters or reactors. We're looking to increase the temperature because with increased temperatures we get increased efficiencies. Therefore, we use less fuel, and that's good. However, when we go to higher temperatures, they're more aggressive environments. So there's going to be more oxidation. So you have to have good structural properties and you have to have good oxidation resistance.
So you can think of high temperature oxidation kind of like you think of rusting on your car, but the extreme example. So you leave a piece of bare iron out in humid air. Eventually, you'll form iron oxide, which will flake off. It's non-adherent. Taking that to an extreme example, when you would put an alloy in a high temperature environment like this with oxygen, nitrogen, the things in the air around, is the oxygen would get in, react immediately with the base materials and turn them into either volatile oxides or oxides that are going to spall and flake off, which obviously you don't want happening when you're flying at very, very high speeds or in your engine because your material is actively degrading. We
have some advantages through the laboratories here at UW-Madison with our additive manufacturing. The additive manufacturing technologies allow us to make a variety of samples and do compositions on the fly. We also have good arc melting capabilities where we can look at these refractory materials. Refractory means typically they're going to melt over 2000 degrees C.
The invention is a high-temperature refractory alloy, ternary of molybdenum, chromium, aluminum, the development of which started with my personal interest in hypersonic aircraft and jet propulsion. So we started the development of this alloy looking at molybdenum alloys, and then we picked 6 or 7 alloys across the phase diagram, and it turns out the one that worked was actually chromium-rich, so we ended up flipping the script a little bit. We started at 1000 C, put all 7 compositions in there and then ramped it up another 100 degrees and started throwing compositions out as they failed. And one of our compositions just refused to die. We got it all the way up to 1600 C, and that's when we really realized we had something special going on with that composition.
The interesting part of this alloy is the first discovery that this has got remarkable properties, and you really don't know why. We can have some hypotheses, but a true development is going to be able to work either with a funding agency or with a company to tailor that specific properties. We have bounds that we can tailor on this for a specific application.
When we set out, we designed for one property. We were just looking for oxidation resistance, which is a lot of how commercial alloys are developed. You kind of are targeting one property, and then you characterize the rest and you tweak it to fit your application. So that would be the next step for us. And that's something we'd be looking to do either internally at UW or with an industrial partner.
Hi, I'm Michael Carey, Licensing Manager with WARF. If you like what you heard and want more information, use the information on the screen or in the description below to get in touch with us. And don't forget to like and subscribe for more great videos from WARF.